Okay, welcome back everyone. In this video, we're going to begin our unit on periodic motion. So in this first segment, we're going to be looking at periodic motion and characteristics of simple harmonic motion. And we want to look at what causes periodic motion and how do we describe oscillations in terms of amplitude, period, frequency, and angular frequency. So one question you might ask is, why do dogs walk faster than humans? Why do children walk faster than adults? Does it have anything to do with the characteristics of their legs? And so these types of motion that repeat themselves, such as pendula, musical vibrations, car engines, etc., these are all periodic motion or oscillation. So what causes periodic motion? Well, if a body is displaced from an equilibrium position, there is a restoring force on it. So in this diagram right here, you can see that the object is moved forward a distance x, but there's a backwards force, Fx, which is pointing backwards towards equilibrium. Okay? So what causes periodic motion? Restoring forces. Because then what's going to happen is that the object will go past the equilibrium because it still has velocity even if it's gone past the 0 point, and now it will compress the spring in the negative direction, and the spring will exert a force on it in the positive direction. So this force is going to cause oscillation of the system, so periodic motion. This restoring force Fx always pushes back towards x equals 0. Okay, so here are some characteristics of periodic motion. First, we can describe the amplitude as the maximum magnitude of displacement from equilibrium. We can write the period as the time for one cycle, and the frequency as the number of cycles per time. So period and frequency are inverse of each other. We can also talk about the angular frequency, omega, which is 2 pi times the linear frequency. Omega equals 2 pi f. Now you might think that this looks like angular speed, and while it's related to angular speed, it is not the exact same variable. It has a different meaning in this context. So we'll talk about that carefully. And we can say that the frequency and the period are reciprocals or inverse of each other. So f is 1 over t and t is 1 over f. So for example, if I have a periodic motion that has a frequency of 5, so it's happening 5 times per second, then that means that if the frequency is 5, the period for one of these will be 1/5 or 0.2 seconds. So, as a quick example, let's say that we have an ultrasonic transducer that oscillates at 6.7 megahertz. So that's 6.7 times 10 to the 6. We want to calculate how long each oscillation takes. So that's a frequency measured in hertz. Okay, hertz is the same thing as 1 over seconds. And we want to find the time. How long does each oscillation take, and what is the angular frequency? So if we just do 1 over f, that's going to get us about 1.5 times 10 to the minus 7th seconds per oscillation. And angular frequency is 2 pi times linear frequency. So we can just say that that's about 4.2 times 10 to the 7th. And that's not hertz anymore, that will be radians per second. Okay, well, let's talk about simple harmonic motion. Okay, simple harmonic motion occurs when the restoring force is directly proportional to the displacement from equilibrium. One example of this would be an ideal spring which obeys Hooke's law. So the restoring force is F of x equals negative kx. So when the force is proportional to the displacement. So force is proportional to x. And so what you can see here is that when the restoring force is positive, the displacement will be negative. So up here, this is like when you have compressed a spring, it'll be pushing back to the right, so positive force. And then when the displacement is positive, that means that the spring will be pulling back to the left. Now this does work to an extent for non-ideal springs. Okay, and we can use an approximation for much of this region right here. Okay, so we know that F is equal to ma, but it's also equal to negative kx. How then do we get to this, and how do we calculate x of t? So basically what we do is we write that ma is equal to negative kx. And what we recognize is that a is really a derivative. It's actually a second derivative. It's the second derivative of position with respect to time. So we went over that in the linear motion unit. That's equal to negative kx. And this equation right here is a special kind of equation. This is called a differential equation. And we've solved differential equations before in this course. But this one is doubly special because it involves a second derivative. So there are whole classes devoted to solving differential equations, and we're not going to go into the details right now. But one thing that we might do is rewrite this as d squared x dt squared is equal to negative k over m times x. We'll just write it like this. Negative k over m times x. Okay? Now, basically what this means is that we want a function x of t such that its second derivative will satisfy this equation. So we can plug in x of t on the right and take the second derivative and plug it in on the left, and it'll basically work out. So to do this, we have to make a guess. We're going to guess x of t, and this is an actual technique for solving differential equations. You guess a solution. So we are going to guess, and you'll see why in a moment. This is a quite educated guess. We're going to guess that this is equal to a cosine of omega t. Okay? So let's go ahead and plug this in. But to do that, we need to get dx dt, which we could also call the velocity. But that will be negative omega a sine of omega t. Making use of the chain rule, the omega comes out when we take the derivative. And then d squared x dt squared is dv dt. Wow, twice in one equation, huh? That's dv dt, which is a, which is negative omega squared a cosine of omega t. And now you're seeing why we picked this, because when we took the second derivative, we got from a cosine back to another cosine. So let's take it and plug it in here. So d squared x dt squared is going to go here, negative omega squared a cosine of omega t. Is that equal to a constant times the original function? The original function would be a cosine omega t. See that right here? There's the original function. Well, it turns out that the original function cancels out on each side, and that means that our guess is a solution of the differential equation if omega squared is equal to k over m. So it is, and we say that omega for a mass on a spring is equal to root k over m. Okay, So this means that we really do have a solution to our differential equation, namely that x of t is equal to a cosine omega t, where omega is root k over m, or it's the angular frequency. That's great. Okay, now another way to think about this is that simple harmonic motion is the projection of circular motion onto a diameter. So if you have like a record player and a ball moving on that record player, its shadow will trace out simple harmonic motion. Okay? Or you could say that the x coordinate of the ball, which is equal to a cosine theta, will move around as time goes by. Okay, and by the way, theta is equal to omega t. Remember that from our rotation unit. Okay, so we talked about this, but if we have a body vibrating on a spring, omega is equal to root k over m. And that comes from our differential equation, d squared x dt squared is equal to negative k over m times x. So k over m was omega squared. And that's what we needed to get this to work. Okay, let's do a quick practice problem and then we'll move on. So a force of 6 newtons causes a displacement of 0.03 meters. And we want to take a 0.5 kilogram glider and pull it and release it from rest. So we want to find the force constant, the angular frequency, and the period of the resulting oscillation. Okay, so first of all, for the force constant, F is equal to negative kx, so 6 newtons is going to be k times 0.030 meters. And so then when we plug that in, 6 divided by 0.03, we're just going to get that k is equal to 200 newtons per meter. Okay, usually the spring constant is force divided by distance. Okay, the angular frequency, that's one of those things where unless you look at it close, you don't even notice it's there twice. So angular frequency omega is equal to 2 pi f, but it's also equal to square root of k over m. So we know that m is 0.5 and k is 200. So 200 divided by 0.5 is 400, and the square root of that is 20. And finally, we want to find, so I think what I meant to do here is to say find the angular frequency omega and the frequency f. So f would actually be omega over 2 pi. So 20 divided by 2 pi would be about 3.2 hertz. Okay, and if I get any more things wrong, it's really going to hertz. My pride, haha. And the period will be 1 over f. So just take the inverse of that, and you get about 0.31 seconds. Okay, so we're going to stop here, and next time we'll do a little bit more practice, and we'll talk about graphs of displacement, velocity, and acceleration versus time.